Hey everyone, and welcome back to PrepFusion. So today we'll be starting the lecture 4C of controllers and compensators. So this will be the final lecture. So in this lecture we'll do a design problem. The last problem of the previous lecture was a design problem. That was a very good problem. If like any one of you has missed that problem, do watch that. That is a very important problem. Okay, that may be asked in interviews. If you say like control system is your favorite chapter, so let's do another design problem. So here we have been given a system, okay, and a controller is given. So let's read the question. Consider the given below plant. Design a lead compensator such that the velocity error constant becomes 15. Okay, what is velocity error constant? I will show you. Like we already know that obviously. And phase margin is at least 50 degrees. So phase margin is at least 50 degrees and gain margin is at least 10 dBs. At least, at minimum 10 dBs. So let me write everything. So I have to design a lead compensator. So GC OS will be a lead compensator. Okay, lead compensator, hence it will be a zero dominating system. Compensator. Okay, so if it's a zero dominating system, they have already given the form of GC and you have to find the value of KC, alpha and tau. So basically by saying that design a lead compensator, basically you have to find the value of KC, alpha and tau. So yeah, and what other information they have given us? Other information is velocity error coefficient or constant is less than 15. Now what is KV? KV is limit s tends to 0 s g of s. Now basically g of s is this whole thing. Sorry, g of s is this whole thing. So let me first write one thing, that my g of s equals to gc of s into g p of s. Okay, so now s g of s, and here element s tends to s g of s, where g of s is equal to gc into gp of s. So this has to be less than 15. So this condition is given. And what is another condition? So phase margin is at least 50. So phase margin has to be equals to or greater than 50. It can't be lower than 50. At least 50 it has told us. So that the margin needs to be more. The more the margin there is, the more relatively stable the system is. So phase margin is greater than 50 degrees and my gain margin is obviously at least 10 dBs, that it is greater than 10 dBs. Gain margin is greater than 10 dBs. So these things, they have told us that we need these things. Design a controller for us. So you have been given the duty that they have given you the system, okay, GP, and you have to design a controller with like ideal cases, like not ideal, with the optimal values of KC, alpha and tau. How will you design it? So like you can obviously pause this video and you can try it for yourself. I will start obviously thinking about things. So like what is the first thing? The easier part is this, velocity constant less than 15, because phase margin is difficult. I have to find the gain crossover frequency, or gain margin is also difficult. I have to find the phase crossover frequency. But velocity error constant is very easy. Just put s g of s equals to 0, and from there you will find a relation. So you have been given 3 relations and 3 unknowns are there. So yeah, obviously you understand, right? 3 unknown, 3 relation. You will be able to find all the 3 values. So first I will go with this because this is the easier thing. So g of s is this. So g of s, I can write kv equals to limit s tends to 0 so it is telling us it becomes 15. I wrote there less than 15. It is actually not less than 15, it becomes 15. So it will be equals to 15 itself. My mistake. Okay, so everywhere I will take the limiting case. Greater than equal to, because from there only I can get an exact value. Because I have to design one thing, right? I have to find values of KC, alpha and tau. So I will get an exact value. I will take the limiting case. So KV is equals to 15. So S times the controller. Now what is this controller? The controller is this. So simply KC into s plus 1 by tau into s plus 1 by alpha tau into the planned transfer function, which is 3 upon s into s plus 2. 3 upon s into s plus 2, which is equals to 15 itself, the limiting value. Now what do? Basically this s will get cancelled. Okay, this s will get cancelled. So then can I put s equal to 0? I can put s equal to 0. This will be alpha and this will be 3 upon 2. So kv equals to, no, not kv, now I can simply write this will be equals to kc into alpha into 3 upon 2 equals to 15. So my kc will be simply, so not kc alpha will be simply 3, 15, 10. Kc alpha equals to 10. So this is one condition, kc alpha is 10. So like how I can write this transfer function? I can write this transfer function in a different manner, in the time constant format. So basically I can write this kc alpha. Okay, I can multiply like alpha tau, like I can multiply alpha tau, take common alpha tau and 1 by tau here. So this will be s tau plus 1 and this will be s tau plus 1. Okay, so yeah, this is the thing. So like my kc alpha is 10, so this value is 10. So this value I got. So now what next? So basically I can write my overall g of s will become 10 times s tau plus 1 s alpha tau plus 1 into 3 by s into s plus 2. Okay, so this is my overall g of s. Now let's first see what is the phase margin currently. Okay, what is the phase margin currently, because they are talking about the phase margin. So we'll see the phase margin currently and we'll see how much do we need to improve. Actually, how much phase margin do we need to improve, because at least it should have 50 degrees of phase margin. But currently how much phase margin do I have? Okay, with all these things that I have to see. So for this obviously I have to find the gain, right? I have to find the gain. So like I have to find the omega gc. I have to find the omega gc. Now can I find the omega gc? I have to make this whole gain equals to 1. Can I make this whole gain equals to 1? No, because I don't know the gains of, like I don't know the values of all this. So I will see the gain without this. Okay, I will see the gain without this. Basically what I will see is, I will see what is my omega gc with just kc into alpha and this transfer function. Okay, when I change my controller kc alpha to 10. Okay, so basically what I'm talking about is that I need to find omega gc. I need to find omega gc for phase margin. Okay, I need to find omega gc for phase margin. Now what is happening here is, if I do the gain formula, like gain formula equals to 1, I won't be able to like evaluate this. I won't be able to evaluate this. So I won't be able to find omega gc. I won't be able to find omega gc. But if I just evaluate this, okay, if I just evaluate this, then what will happen? This is a lead compensator. So if this is a lead compensator, what does a lead compensator do? Lead compensator basically if I draw the Bode plot of lead compensator, initially it is some constant, then it increases, okay, then it reduces, then I mean it stays constant. So for a lead compensator here, it's a zero dominating system, 1 by tau, and this is 1 by alpha tau. So for lead compensation, I see the gain is increasing. Here the gain was initially what? Initially the gain was kc, 20 log kc. So 20 log Kc alpha, and here the gain will be, if I put s equals to 0, yeah, 20 log Kc alpha, here the gain will be 20 log Kc. Okay, so what is happening is that I will find my omega Gc with only this thing. So I found my omega Gc. Now I found that omega Gc. Now if I put this equation, so let me write few things. So first let me take a new g dash of s, which is 30 upon, like Kc alpha is this, right? That's why I took this 30 here, because Kc alpha is 10. So I'm taking the 10. That is fine, because that is known to us. But these things are not known to us. Is not known to us, I will talk. Just hold on a second. 30 upon s into s plus 2. I'm naming this as g dash of s. Now from here, if I found the magnitude g of j omega, omega g, this is omega gc under root omega gc square plus 4. Okay, okay. So next what I want to say is, what is g magnitude of g of j omega, not g dash. So magnitude of g of j omega is this same thing with another thing included, 30 upon omega into under root omega square plus 4. Also this is included, so this is omega tau whole square under root plus 1. Let me just move this more further forward. Omega alpha tau whole square plus 1. So basically I found this omega gc. Now if I put this omega gc over here, this will be equals to 1. This will be equals to 1. Now what will be the value of this? What will be the value of this? The value of this will be something more than 1. Something more than 1, right? Something more than 1, the value of this. Why will it be something more than 1? Because this is alpha. Alpha is less than 1. So overall this value will be more. Overall this value will be more. So my omega has to increase further. So if I put magnitude of g of j omega at omega equals to omega, let me not write this as gc like on normal gc, let me write this as gc dash omega gc dash. So if I write this as gc dash, this will be omega gc dash. Now if I find the magnitude of this, what will happen? Basically this will be equals to 1. This will be equals to 1. So 1 into this under root omega gc tau whole square plus 1, not gc dash, and omega gc tau into alpha whole square plus 1. Now what do we know? Alpha is less than 1. Alpha is less than 1. So overall this thing will be less than this. So if alpha is less than 1 for a lead compensator, okay, alpha is less than 1 for a lead compensator. Now if alpha is less than 1 for a lead compensator, that means omega gc tau alpha should be less than omega gc dash tau. That means overall this is higher. So if this is higher, overall this gain will be something more than 1. Okay, so this is not the actual gain crossover frequency, not the actual gain crossover frequency. One. So this is not the actual gain crossover frequency. So what needs to happen? This will obviously provide always something gain more than 1. what needs to happen is I have to further increase my omega GC. If I further increase my omega GC, then this will reduce, so this will be something less, so it will go to 1. So I need to increase my omega GC. So actual omega GC of this G of S will be something greater than omega GC dash. Okay, I need to increase my omega GC. So like this is what I wanted to tell you, that we have to increase our omega GC. But obviously we can't get this omega GC without finding the parameters. So we will find our omega GC dash, and from there we'll take few assumptions. So whenever there is a design problem, you have to take few assumptions. Okay, so yeah, let's find omega GC dash. So what is omega GC dash? Basically the G of j omega magnitude equals to 1 at omega GC dash, that we already know. So basically (30 upon omega GC square plus 4, not 1. Okay, so yeah, plus 4. So basically this is equals to 1. So again we have to assume x, omega GC square equals to x. So I will do the whole square, 900 by, we'll assume that omega GC dash square, this is dash square equals to x dash square, or simple x square. So this will be x square into x square, sorry, this will be not x square, this will be x only, else it would be same, right? X plus 4 equals to 1. So x square plus 4x minus 900 equals to 0. Okay, so x square plus 4x minus 900 equals to 0. Now this is a quadratic equation, so we'll solve this. X equals to minus b plus minus b square minus 4ac plus 3600 divided by 2a. Okay, divided by 2a. So like if I solve this, what will happen? It will be almost like 60 only, 60. So 3600 plus 16 under root. Now obviously we will ignore the negative solution. We'll ignore this negative solution. Why? Because this is equals to what? Omega GC square, and omega GC can't be imaginary. So like under root of a negative will be a imaginary term, which is not possible. So we'll ignore the negative sign. So we'll only take the positive sign. 60.3 minus 4 divided by 2 equals to 28.67. X is equals to this. So what is my omega GC dash? Omega GC dash equals to under root of x. So it is equals to 5.29. Okay, it is equals to 5.29 radians per second, or you can say it is almost equals to 5.3 radians per second. Okay, so yeah, this is equals to 5.3 radians per second. So this we found out. Now here what we'll do, we'll find the phase. We'll find the phase at this angle. So from here we'll obviously find the phase margin, right? So from here I will find the phase margin. So basically what I am trying to tell you is this Kc alpha is providing it some gain. Kc alpha is providing it some gain. Where is it? This Kc alpha here, Kc alpha is providing it some gain, that knob we are controlling, and this rest is giving it some angle. So I will talk about this angle later, but first I have found the gain, and from there I am finding the omega GC, and from there I will find the angle. So also I will explain few assumptions that we have taken so far now. So I will find the phase margin without the compensator now. Without the compensator I will find the phase margin at this particular frequency. So phase margin is what? Phase margin is 180 degree plus angle of g dash of j omega at omega equals to omega gc dash. So this is not the actual phase margin, okay, this is not the actual phase margin, this is the uncompensated phase margin, uncompensated phase margin. So I have to find the angle. So what is the angle? So this will be simply, if I find the angle here, what is the angle, angle, where did it go, where did the transfer function go? Oh no. Okay, have I wrote even the transfer function? This is the transfer function, right? So if I convert this into g of j omega format, so this will be 30 j omega into j omega plus 2. So the angle for this will be minus 90 minus tan inverse omega gc dash by 2. Okay, so angle for this is 90 minus omega gc dash by 2. So if I put omega gc dash equals to 5.3, so let's see what it comes up. Tan inverse oh no, minus 90, I made some mistake in the gate calculator. So this will be 1 minus 159.318, okay, degrees. Now what is the phase margin of the uncompensated system? It is around 2.68. So it is obviously less, obviously we have to make it more. So phase margin is less, we have to make it 50 degrees at least. So we have to add phase lead equals to how much phase lead we need to add? We need to add a phase lead of 50, right? So we need to add a phase lead of minus 50, 29.32 degrees. Okay, now we need to add this much amount of phase lead to this. Now what we can assume is that our lead compensator add this much, like the maximum phase that our lead compensator adds is this much amount. Now what will be the issue with that? The issue will be that, let me first write, assume maximum (29.3 degrees). Okay, now if you assume this, what will the problem? So I have taken 29.3 degrees, but my omega gc is not the actual omega gc. My omega gc is not the actual omega gc. Okay, but actual omega gc is greater than omega gc dash. So what will happen here is that, just hold on a second, I've got a call. So basically, as I was saying, that this omega gc is greater than omega gc dash, hence what will happen, my effective angle omega g dash, where is it, omega g dash of, my effective angle omega g dash at j of g omega at omega gc, as gc is greater than this, hence if I put the same thing in this formula, omega gc dash will be more, so this will give me more phase lag. So if this is more, now the magnitude difference won't be much. Okay, the magnitude difference won't be much. This magnitude difference won't be much, as like this omega gc and omega gc dash difference also won't be much. This will be almost near about, but as this is more, then this omega gc dash at omega gc will be further lower. Okay, further lower, okay, than this. I should write here omega GC. Okay, so this will be lower, hence obviously the phase margin will be even lower here. So phase margin will be even lower as this is contributing to more phase lag. So phase margin, actual phase margin will be even lower than this phase margin. Okay, so if this is lower, then what will happen? Obviously we have to provide extra lead, not just this 29.3, we have to provide extra. So hence we provide, like this is a design concept, basically we provide, just for a safety of margin, we provide extra 5 to 6 degrees of phase lead. So let me tell you, this is not obviously gate problem, this is a design problem. So like this won't be that much needed in the gate examination, but few of the concepts may be like good to go, right? So this is the last lecture, that's why I am just doing bit of things extra. So yeah, so what is my phi m? So like then I will assume that my phi m, maximum phase that the lead compensator provides, is 35. So this is a design problem, so obviously you can assume anything. I'm assuming 35 degrees. Okay, so and the where does it happen, when does it give maximum phase? So it gives the maximum phase at the frequency omega m equals to 1 by tau under root alpha. So it gives maximum phase at 1 by tau under root alpha. So from here we will find the tau and alpha. Okay, so if the maximum phase is this, then we know one formula for a lead compensator for the maximum phase, which is phi m equals to sine inverse 1 minus alpha divided by 1 plus alpha. So sine phi m will be equals to this. So basically sine phi m is what? Sine 35. So let me just write sine 35 equals to 0.5736 equals to 1 minus alpha and 1 plus alpha. What I can do is I can simply like subtract this and add this in the bottom. So by subtracting, what I will do is 5736 minus 1, basically componendo and dividendo. So this is by 1, right? And 1 plus 0.5736. This is equals to this. I should write in front, and this I should write. This is minus 2 alpha, and this is alpha, 2 simply 1, no sorry, not 1, simply 2. Okay, so I'm simply subtracting the numerator from the I'm subtracting the denominator, I'm subtracting numerator from the denominator, and I'm adding denominator and the numerator. Okay, so yeah, componendo dividendo. So my alpha will be simply, just hold on a second, divided by 1.5736, which is equals to 0.27. Now I want my gain crossover frequency, where I need a phase margin of 35 to occur at this omega m, because this omega, like the compensator is providing this 35 degrees angle at that frequency only, So I want this frequency to be equals to gain crossover frequency, because at that frequency I need this 35 degrees. So my omega gc will be equals to omega m. Now this omega gc is not my omega gc dash, because omega gc dash was without the compensator. Now I have the compensator, I have to accommodate the gain of that compensator also. So which is equals to 1 by tau under root alpha. Okay, 1 by tau under root alpha. So basically this will be equals to simply what is it, where is it? So what is my g of s? If I can find it somehow, if I can find it, where is it, where did it go? Yeah, here is it, right? This magnitude, I'll just copy this magnitude. Okay, now if I put this at omega m, this should be equals to 1, because this is what I'm talking about. So omega g should be equals to omega m for this compensated system. So for this compensated system, if I put here omega m, what will happen is 1 by tau under root alpha, this will be, tau will get cancelled, this will be alpha square plus 1, and here also I will have 1 by alpha square plus 1. Just hold on a second. So this will be simply under root 1 by alpha plus 1 divided by under root, I can take this whole over under root thing, one by under root alpha. So this is like alpha plus 1. So now what I can write is okay, this one will get cancelled, right? Basically this will be under root 1 by alpha into like 1 plus alpha divided by 1 plus alpha. So this one will get cancelled, only 1 plus 1 by alpha under root 1, like 1 by under root alpha will be remained. So overall these thing will be 1 by alpha at this frequency. Okay, 1 by under root alpha. So I can write 30 by omega gc into omega gc whole square plus 4 equals to 1 by under root alpha. Now 1 by under root alpha is, alpha we know already, we have already found out alpha is 0.27. so I will put the 0.27. okay, I'll take the under root, I will take it to the other side, and reciprocal 1.92, and I will divide it with 30. So this will be 15 point something, 15.617 equals to, I will take the whole square, omega gc whole square, sorry there was an under root here also, sorry, plus 4. So yeah, obviously we'll need extra pages, just hold on. So I will again assume my omega gc to be equals to omega gc square equals to x. So if I just square this, what will this become? So this one, okay, am I making any mistake over here? Just hold on a second. Okay, this is 0.27, take the under root, and I okay, yeah, and I multiply this with 30. Yeah, this will be 50, sorry, this will be 57, not 57. This will be increased, not decreased, because here something lower value is getting divided. Now the square of this will be 3333. So simply it is like the equation will become x square plus 4x minus 33.33 equals to 0. Now simply you use the quadratic Sridharacharya formula, minus 4 plus minus b square 16 plus 4 ac, so into 4 into 33.33 divided by 2, so plus 16 and under root, then we do the we only take the positive solution, because like taking the negative solution, it will not yield us, it will yield imaginary omega gc, which is not possible. So we'll take the positive solution, minus 4 divided by 2, so which is equals to 55.77 x. X is equals to this. Now I will take the under root to find omega GC. The under root of x is 7.46. Okay, 7.46. So you see that like initially what was like, it was 5.3 and it is 7.46. Not much of difference. I know it is a bit of difference, but like that is what design problem is, right? You have to take in assumptions. So it is omega GC equals to 7.46 radians per second. Okay, now what you do from here, you can simply find the value of tau. So omega GC is equals to omega m equals to 1 by tau under root alpha, which is equals to simply 7.46. Now tau will be simply 1 by 7.46 into under root 0.27. So if I just multiply this is 0.27 under root, and if I just do this, then this will be almost equals to 0.2577 seconds. Okay, so this will be my value of tau. So basically what will be my final values? Final values will be GC of S. I wrote this as KC alpha S tau plus 1 divided by S alpha tau plus 1. Okay, S alpha tau plus 1, which is equals to, what is KC alpha? KC alpha was 30. Okay, KC alpha was KC alpha was 10. The overall gain was like that 30, but this was 10. Now what is S? Like S into tau, so this is 0.2557 S plus 1, and what is this? S alpha tau, so I will multiply alpha with it, 0.27. This one will become even lower, 0.0696 S plus 1. Okay, so I can write this as almost 7. Okay, so this is the case. Now here, like what is happening here? So with this introduction of this like lead compensator, obviously I told you that omega GC is increasing. Like lead compensator omega GC is increasing. Okay, omega GC increases, what happens? Like the bandwidth also increases with compensation. So these two things increases, omega GC and bandwidth. How does the bandwidth increase? Because as I can see, it is providing amplification. Right? If it is providing amplification at higher frequencies, at lower frequencies, that is fine, it is not doing anything. But at higher frequency, it is providing amplification. So obviously, it is shifting up. So obviously, overall, the graph of this overall G of S will be something like this. So let me draw this. If I cascade these two, what will happen? In dBs, it will shift them up, the overall G of S magnitude. So if it shifts them up, then overall my bandwidth will increase, because the bandwidth was that, like you can set bandwidth anything from the DC gain, how much where it goes to, or like where it is 3 dB down from the DC gain. So as this is shifting up, right, this is adding some gain. So obviously the 3 dB down point will come later. 3 dB down point will come later. Okay, that's why my bandwidth is increasing. Now that is a good thing. But if bandwidth is increasing, also another thing is bad, that it is amplifying high frequency noise. Amplifying high frequency noise. Okay, so it is amplifying high frequency noise. So if it is amplifying high frequency noise, then that is not a good thing. Right? We don't want to amplify high frequency noise. But also what other thing is happening? It is giving me like lower loop gain at low frequency. Where is the graph? Where is the graph? Here. Like at low frequencies, it is attenuating. So at low frequencies, it is attenuating. Low frequencies, low frequency gain is low. So gain is low. That means I have to make Kc alpha high. Kc alpha high. Okay. Gain is low, Kc alpha high. So if I have to make Kc alpha high, that means I have to like bring a better amplifier. More gain I have to provide. So more gain. So if I have to provide more gain, obviously it will be more costly to me. So while designing a system, obviously you have to take consideration of the cost also. So more costly. So I want to come to this cost section at the end, because that is the main thing. Whenever you will design, like you will go to MTech and do this thing, right? You design something. So obviously you have to take in care of this cost factor as well. So whenever you are going to design anything, always the engineer should have the technical abilities and also this cost abilities. That's why we study economics and all those things, right? So economics is also very important. So you have to take care of this cost factor also. So you can't increase the gain too much. So you have to balance out other parameters. So that's how you design. So you found this final design, then again you reiterate, then again you go back, and then again you put these values, and then again you reiterate that what will be the optimal value. If I can increase this Kc alpha further, and I can change other parameters, tune other parameters to get a better optimal solution, so that my cost will be lesser. Okay, ultimate thing is cost. So yeah, so that is it for this lecture basically. So I hope you like this whole control series like lecture series, and I hope you can solve all your questions. So in the previous lecture I also like told a few things, and I won't repeat again. So I will see you with a new subject. Okay, and I hope you enjoyed this whole series, and yeah, do share with your friends, and like whoever preparing for GATE, I think this is a like total comprehensive course that I have taught you, and free you won't get anywhere. So okay, on YouTube in free you won't get this type of content anywhere, I can assure you that. So yeah, thank you for watching. I will see you in the next video.